All right, let's jump right in. Today, in this explainer, we're diving into a really fascinating piece of the analytical puzzle, how exactly modern scientific instruments translate physical chemical events into the digital data we read on our screens. We are going to specifically look at the inner workings of recording integrators and specialized data treatment software. It's a pretty incredible journey, taking a literal physical reaction in a lab and turning it into a precise number on a microcomputer.
Because think about it for a second. We live in an entirely analog world, one that's full of continuous, flowing variables. But computers, well, they strictly speak digital. They only understand those discrete, coded units of zeros and ones. So it begs the question, how does a computer actually see a chemical reaction? Setting up that fundamental translation problem, bridging chemistry and computing, is absolutely crucial to understanding how modern analytical measurement actually works.
Here's a quick look at our roadmap. We'll cover the analog signal problem, then analog to digital conversion, building the digital histogram, calculating the peak area, and finally, why we moved beyond manual methods. Okay, section 1, the analog signal problem. So whenever a chemical reaction takes place, say inside a chromatograph, the output from the detector is a continuous, low-level analog voltage. We're talking microvolts or millivolts here. The tricky part is that this continuous signal has to be intercepted and translated before a microcomputer can do anything with it. If we don't translate it, the computer is basically completely blind to the chemistry happening right in front of it. Which brings us to section 2, analog to digital conversion. Let's actually trace the physical journey of that signal, because the hardware sequence is super interesting. Step 1, the detector spits out that raw analog voltage. Step 2, the signal travels right through an interface card linked to the computer. Step 3, and this is the real magic trick, an ADC circuit samples that continuous signal incredibly fast. And finally, specialized data treatment software processes those resulting digital values. Now, that ADC circuit, the analog to digital converter, is literally the star of the show. We are talking about a sampling frequency of a few hundred hertz. Why so incredibly fast? Well, if you're using capillary columns, you're going to get some extremely narrow chromatographic peaks. If your ADC circuit isn't slicing that signal hundreds of times a second, it's going to completely miss the peak, and your area measurements will be totally off. This conversion happens right at the input of the recording integrator. Moving right along to section 3, building the digital histogram. So once the signal is chopped up, how does the software picture it? Think of the histogram metaphor. Instead of one smooth, sweeping Gaussian curve coming from the detector, the data gets sliced up into these blocky, calculable time intervals. The chromatogram gets stored in the memory simply as numbers that correspond to a series of discrete rectangles. It's basically a digital mosaic of the chemical reaction. To actually build out that histogram, the software treats those digital units as elementary areas that are bracketed by a specific time interval. But here's the catch. A rectangle needs a bottom edge to be a closed shape, right? To solve this, the software uses a reference signal to determine the baseline in a totally artificial manner. This is absolutely crucial because it lets each individual time rectangle completely close off. Once they are closed, every single element of that histogram is prepped and ready for calculation. Section 4, calculating the peak area. At this point, the chromatogram is just sitting in the microcomputer's memory as a bunch of numbers. To figure out the actual amount of a substance, the recording integrator calculates the final peak area. And it's pretty straightforward. It corresponds directly to the product of the units chosen for each axis. So if your y-axis is measured in picoamps and your x-axis is time in minutes, your area units are literally picoamps multiplied by minutes. It's just simple geometry built out of thousands of rapid-fire data points. But obviously, the software does way more than just multiply two numbers together. While different models have their own quirks, all of these instruments and specialized software suites pack some serious computational power. For instance, they automatically perform baseline correction if things start to drift. They can accurately treat negative signals without throwing a fit. Plus, they come loaded with built-in calculation and integration methods to guarantee that our digital histogram perfectly mirrors the chemical reality. Finally, section 5, beyond manual methods. To really appreciate just how good we have it with modern data treatment software, we have to look back at the wildly tedious manual methods of the past. Before recording integrators were everywhere, lab techs actually used a manual triangulation method to measure Gaussian eluting peaks. The formula? You took the width of the peak at half of its height and multiplied it by its total height. They were literally treating a complex chemical signal like a simple triangle drawn on chart paper. Fortunately, that manual method is completely out of use today, and for good reason. A chemical peak isn't a perfect triangle, it's a bell-shaped Gaussian curve. By just multiplying the width at half height by the height, technicians were routinely missing data. In fact, that manual method only ever accounted for about 94% of the total area of the peak. Today's recording integrators capture basically all of it, completely closing the gap on that missing 6%. It's honestly mind-blowing when you think about it. We went from manually measuring paper charts with a ruler and missing 6% of our data while doing it, to having ADC circuits slice a continuous chemical signal hundreds of times a second into flawless digital histograms. As we wrap up this explainer, it definitely leaves you wondering, as software gets even smarter and faster, what completely unseen details of chemical analysis will we be able to measure next? Thanks for tuning in, and keep asking the big questions about the science behind the data.